Hi everyone, in this presentation I will give a brief summary of my research about bidirectional evolutionary structural topology optimization for 3D printed FRPs. So to talk about topology optimization, I must take you back to the first spark for structural optimization. In 1904, the Australian engineer Anthony Machell wrote an ingenious paper with the title Limits of Economy of Material in Frame Structures. He basically developed a new way of identifying the optimal configuration of a truss, how to use less material for better performance. In 1904, his work was clearly ahead of its time, as there was no practical way for manufacturing his structures, even though his structures uses less material. Therefore, his work was considered only an academic diversion and kept on the shelves for 50 years until it appeared again in the 1960s, leading to the development of multiple topology optimization methods, one of which is BESO, which is the one I'm working on right now. So, what is structural topology optimization? Hung and Chi gave a nice definition for structural topology optimization. They said it's the process of optimizing the topology of a volume to obtain optimal structural performance under pre-specified constraints. And I like to define it with less words. It's basically to do more with less. Over the last decades, multiple topology optimization methods have been developed for isotropic continuum structures, such as the density-based method or the level set method or bidirectional evolutionary structural optimization BESO. All the methods that I have just shown assume an isotropic nature for the material. And as you know, fibre-reinforced polymers are not isotropic. Therefore, we need a new approach that takes into account the anisotropy of the material. Thus, this thesis aims to develop a robust algorithm using BESO approach to identify the optimal material distribution and fiber orientation under predefined boundary conditions. Also, to develop a practical way of converting optimized models into printable G-codes. Also, to assess the structural elements produced by this approach, meaning with consideration of fiber direction, in comparison with the optimization without consideration of the fiber direction. So, the problem formulation of BESO for 3D printed FRPs is to find an optimum fiber and material configuration within a given volume to minimize the compliance of the structure. This can be expressed as follows. The objective function is to minimize the mean compliance, which equals to the transpose matrix of the external forces multiplied by the displacement over 2. And the objective function is subject to a volume constraint. So the algorithm will try to minimize the compliance while maintaining a certain volume V star. Vi is the volume of one element in the model, and xi is the density or the thickness of that element. It's either 0 or 1. And we got the material orientation or the fiber orientation ranging between the angle 90 and minus 90. This flowchart shows us how BESO for 3D printed FRPs work. At first, we start with defining the design domain, loads, boundary conditions, and the finite element mesh. Then, we define the optimization parameters, such as the evolutionary rate and the filter radius and the target volume. Then, to account for the mechanical properties of the orthotropic material, we need to optimize the fiber orientation. To do that, we need to perform a finite element analysis and calculate the principal stress directions in each element. Then, update the material direction in each element to be in line with the principal stress direction. Then, after optimizing the fibers, the algorithm will proceed in a regular BESO optimization. So what we did here is that we let BESO take into consideration the orthotropic nature of the material and produce the optimal configuration for fibers as the extreme energy values are accomplished when the principal direction of the material coincides with the principal direction of the stress and strain. Similar to the 100-line code of Zhu and Chi, the algorithm was constructed using Python with Abacus scripting interface. However, BESO for 3D printed FRPs has 3 more novel pieces of code. The first one is for discretization and adding the variable of material orientation in the optimization. The second one is for identifying the principal stress direction for each element. And the last one is for updating the material directions. And there is minor changes of the code of Zhu and Chi for it to optimize 3D printed FRPs. And here is the results of this approach. In this example, I used a Messerschmitt Bulko Bloom beam to be optimized in 3 different setups. The graphs shows only the right half of the beam. A uses a BESO isotropic optimization with isotropic material with modulus of elasticity of 10 gigapascal and Poisson ratio of 0.3. B have an orthotropic material with these properties, but with no fiber optimization. The main direction of the material is in this direction. C is the results of this algorithm, of this approach, BESO for 3D printed FRPs. And it has orthotropic material properties, but with fiber optimization. All 3 models have the same optimization parameters, with 0.4 for the target volume, and 4 millimeters for the filter radius, and 0.02 for the evolution rate. Let's see how it gets optimized. As you can see, the results are drastically different. The result of A cannot be an optimal for anisotropic material, as it's very different from C. B, on the other hand, compromises a lot on stiffness due to the fixation of the material orientation. In fact, C is 2.5 times stiffer than B, as you can see in this graph. So, this is the optimal structure with the fiber direction in red. And to 3D print this beam structure, we need to smooth it out first. And this can be done using a blurring technique. Then, on Rhino 3D, I was able to make a multi-offset technique for the toolpath, which is very in line with the fiber directions. Then, with the toolpath, I was able to print a proof of concept of the optimized MBB beam. All in all, up to this point, I was able to keep up with the research plan, and in the coming days, I'll try to focus on testing the algorithm for various applications and setups, and I will try to validate my approach using the data that I will have.